Today we're talking in section 6 about natural logarithms and the natural number e. Now, we haven't talked about the number e before. You've only ever talked about the number pi, but e is another number that's irrational, and we are going to use the number e to describe a number of exponential functions as we move forward, and it's often used for growth or decay in a function. Now, what is the number e? It is found by evaluating the growth or function of 1 plus 1 over x raised to the power of x, and that equals 2.71828. Now, just as a general concept here, if you go to your calculator and you look above the natural log, which is right next to the number 4, so you access like a second e, and then you raise that to the 1, your calculator will compute the number e for you. As you can see there, 2.718281828, and it is irrational, and it does keep going. Just to show you, we can multiply that by 1,000, and you will see that that number grows, but because of our decimal here doesn't keep going, it is going to be irrational, and it is going to then have to kind of go from there. So let's go back to our main piece there, but it is an irrational number. You need to just kind of realize that and accept that fact. Non-repeating, non-terminating. So below, I've graphed on the program Desmos on our calculator the blue function, which is e to the x. You'll notice a couple key ideas. It does go through like a normal growth function, that function of 0, 1, and then over at 1 it is up at 2.71828, etc. So the inverse of the function e to the x is called the natural logarithm. And the natural logarithm is written with y equals ln of x, or y equals the natural logarithm of x. And the natural logarithm of x has an assumed base of e. So if it wasn't assumed, it would be written like this. But because you have that natural ln function, you don't need the e, and just we say natural log of x is assumed to be log base e of x. And so it's a shortcut to write log base e, just writing the natural log. So just a very simple shortcut to write log base e. Instead we write it the natural log. And down here you can see in red I've graphed the natural log of x function. And I hope you can see it as a perfect inverse over the green dotted line of our function e to the x. And so it is a very standard logarithm. It's used most commonly as we move upwards in pre-calculus and calculus and onwards. And very limited use of the actual log is going to happen, and the natural log is going to naturally take over and go from there. So what I want to show us today is some ideas around logarithms and review some logarithm ideas as well. So first of all, we need to understand that the properties of logarithms are the exact same with natural logs as they are with regular logs. So here's our first idea. If we have the natural log of m times n, we can rewrite that as the natural log of m plus the natural log of n. Exact same property of adding outside a logarithm is multiplying inside a logarithm. The quotient property therefore says the natural log of m minus the natural log of n. Subtraction outside a logarithm becomes division inside a logarithm. And then finally, the power property says an exponent inside a logarithm is going to become a coefficient out in front of that logarithm. So we have the same three properties of logarithms for natural logs as we do for our regular logarithms. Now let's look at example 2, or example 1, where our goal is going to be rewriting these logarithms as a single logarithm. So as we start out, very straightforward, that is going to be 12 squared minus the natural log of 9. As you know, 12 squared is 144 minus the natural log of 9, which leaves us with the natural log of 144 divided by 9. And 144 divided by 9, hopefully you realize, is 16. And so that's my exact answer, the natural log of 16. Now we could evaluate this on our calculators, so let's flip to our calculators and let's find the natural log of 16. The natural log button is right next to the 4, so the natural log of 16, very simply, is 2.773. 2.773. So let's just write that down as an approximation, or 2.773. And that's our approximate answer versus our exact answer in blue. Let's come over here and look at our next one. We have 5 natural log 2 minus the natural log of 4. So that's the natural log of 2 to the 5th minus the natural log of 4. So that's the natural log of 32 minus the natural log of 4. So that's the natural log of 32 over 4, which is the natural log of 8. Once again, we can come to our calculator. We can find the natural log of 8 as a number 2.079. So 2.079 will be our approximate answer versus the natural log of 8 being our exact answer. All right, let's keep going here. Moving down, we have now the natural log of x plus 3 natural log of y. Well, start off just like normal. The natural log of x is going to be the same plus the natural log of y cubed, which is going to give us a combined the natural log of x, y cubed. And that's going to be our answer. On D, we have the natural log of 8 squared minus the natural log of 4 cubed. So that's the natural log of 64 minus the natural log of 64. So we're going to take the natural log of 64 over 64, which obviously you know is 1. And here we have the same kind of situation as we talked about yesterday. Anytime you take a log of 1 or the natural log of 1, remember that is equal to 0. So our exact answer is going to be the same as our approximation here. That is going to be equal to 0 because our base, e raised to what power equals 1? Well, I think you can obviously see that value is 0. All right, so there's some examples of how to simplify our logarithms into a single logarithm. Very straightforward and easy to kind of work through there. Let's look at our next problems. In our next section, we're going to talk about solving a logarithm, much like we did in section 5, except we're going to be talking about natural logarithms. Simple rules, you should seem familiar. We're going to move the natural logarithms to one side and all other numbers to the other side, combining then natural logs into one natural log function, and then likely have to transform the equation into exponential form. Down below, we have our transforming equation, which should look very familiar. Remember, you have a base right down here of e, so e to the c equals a. And I'm trying to stay away from x's and y's here, so you're not confused no matter what kind of variables you have. All right, so let's look at these 4 examples that we have here. Our first one is the natural log of 2x equals 10. Remember, your base is e, so e to the 10 equals 2x. So e to the 10 divided by 2 equals x is our exact answer. Let's go to our calculator and let's find e to the 10 divided by 2. So let's go to our fraction button. Then we're going to go to our e function, which is above the natural logarithm. So second e raised to the 10 divided by 2. All right. So our answer is 11,013.233. 11,013.233. So we're going to write that down. 11,013.233 is our approximate answer for this. The reason it's so large is because you're raising something to the 10th power. All right, let's take a look at B. Here we have e raised to the fifth equals 3x plus 4. So e to the fifth minus 4 equals 3x. So e to the fifth minus 4 over 3 equals x is going to be our exact answer. Let's go to our calculator. E to the fifth minus 4 over 3. So we're going to go to our fraction once again. E to the fifth, so second e raised to the fifth minus 4 all over 3. Just want to check and make sure that that's what we're doing here. E to the fifth minus 4 over 3. It certainly is. So let's hit enter. And our answer is going to be 48.138. 48.138 will be our approximate answer versus our exact answer up in blue. All right, moving down. Our next problem we have actually written twice for option 1 and option 2 because it presents us with some different possibilities depending on how you want to interpret the problem. The first time we're going to do the problem and just say e to the fourth equals 3x squared. Well, then we need to divide by 3 equals x squared, and then we're going to take the square root of that, e to the fourth over 3 equals x. When we evaluate that on our calculators, the square root of e to the fourth over 3, let's take a look at what that is a value. Once again, our fraction mode. Let's go to e, second natural log, e to the cubed root, or e to the third, over 4. That equals that number. And then I'm going to raise that to the 1/2. And so my answer is 2.241. So 2.241 is my approximate answer for this problem. 2.241. Now, in working this out last night, I also realized some people might want to first try to expand this to isolate the x more, and I wanted to see if that was also a possibility. So we can realize this is really equal to the natural log of 3 plus 2 times the natural log of x equals 4. Therefore, if we're trying to isolate the natural log of x, that would equal 4 minus the natural log of 3. And the natural log of x would therefore equal 4 minus the natural log of 3 all over 2. So my answer would be e raised to the 4 minus the natural log of 3 all over 2, and that would equal x. That would be another way to express the exact answer. And you have to say, is this actually equal? Well, let's take that and let's put that into our calculator to see if we actually have the same value. So to put this into our calculator, we're going to go to the e function. So second e to the x. Then I'm going to go to the fraction button. So we have our e to the fractional button now. Looks like we have an error here. So we're going to clear this out and start over again. All right, let's go second e to the x, then go to our fraction button. Now we're going to, in the numerator, we're going to put 4 minus the natural log of 3, close parentheses. In the denominator, we're going to put our 2. There we have our function. So we're going to hit enter. And you see we get 4.266. So we have to say, okay, is it really the same? Is it different? That's a really good question. We're going to pause the video right here. Okay, well, we're back now. And I had to do a little bit of checking, and I realized that on our first example, that when we plugged in our values, we did not have the correct inners into here. Just to show you the difference here, it needs to be e to the 4th over 3, and that's what I plugged in. And so this 2.241 is actually incorrect. I apologize about that. And our correct answer is going to be 4.266. And you can see we have both of our functions here, 4.266 for both of our answers. And either way, we do that. And so I just found it interesting as we're working through those, that 4.266 is going to be the same value for both of our problems, no matter how we actually work it out. And so long as you follow the properties of logarithms, everything should work out cleanly. Apologize for that little pause there. Let's come back here. All right, well, our third idea is going to be using the idea of exponential functions with e's, and then we're going to try to solve those for x like we did just in the last part of section 5. So we're going to move all the e's to one side, all numbers to the other, write the equation using a natural log, and then solve for x in our calculator or as an exact answer. So here's our first one. We started off very straightforward. E to the x equals 15. Well, if you think that's the natural log of, going to be the natural log of 15. Try to stay in blue here for our exact answers. The natural log of 15, therefore, equals x, because e to the x equals there. So that's our exact answer. And then the approximation for the natural log of 15, very simple and straightforward, 2.708. 2.708. Okay, so we've got two different possibilities here. One is a natural log exact, one is an approximation. Let's look at our second one. We have e to the x over 2. Obviously, you're going to add that over and have that equaling 10. So now you're going to take the natural log of 10 equals x over 2, and that means you have 2 times the natural log of 10 equals x. You could leave that as your answer, or you could say that it's natural log of 100 equals x. Both of those would be considered correct solutions. Either way, the natural log of 100 is going to be 4.605, and just to show you, that also equals 2 times the natural log of 10. So in both cases, 4.605 is going to be our value, 4.605. I'm going to put that in red as our approximation. Trouble writing here, sorry about that, 4.605. So there's our approximation. Let's look down here at our last two. We have e to the x minus 2 equals 8. So that's going to be rewritten as the natural log of 8 equals x minus 2. And so we're going to add the 2 over. So 2 plus the natural log of 8 equals x. I like to put the 2 in front just so you don't think it's the natural log of 10, which it is not. So if we evaluate that, then 2 plus the natural log of 8 as a function, that's going to be 4.079. So pretty straightforward there in terms of evaluating 4.079 for our approximation. Let's take a look at our last one. Once again, isolating, we have 2e to the 3x equals 8. You're going to divide both sides by 2, so e to the 3x equals 4. So you have the natural log of 4 equals 3x. So the natural log of 4 all divided by 3 equals x. Now this is not the natural log of 4/3. I need you to understand that. This is the natural log of 4 and that answer divided by 3. So let's find out that value. Let's go into our fraction. In the numerator, we're going to have the natural log of 4. In our denominator, we're going to have all of that divided by 3, giving us a value of 0.462 as our approximation value. So 0.462 as our approximation. So let's kind of look at a summary of this page. We've got transformation from exponential into logarithm and then using our approximations. On our previous page, we've got transformations from logarithms into exponentials to solve there. And then on the first page, we've got using the properties of logarithms, which are the same three properties as we had before, and working those through to make sure we get our values. So three different ideas, very, very similar to logarithms. I think you're going to find these similar. Our homework here is just going to be 1 through 9 odd and 15 through 27, which I've put down here on this final page. So we're going to use the rest of the time to work on this material. I hope you've enjoyed this and it makes quite a bit of sense for you.